Welcome back. In this lecture, we'll discuss the procedures for obtaining modeling and prediction rules from the governing equations and the boundary conditions. We have stated earlier that the business of similitude is to determine the conditions under which we can predict the values of the dependent quantities, variables, or parameters for one set of independent parameters from those obtained from an experiment, physical or computational, with different though related values of the independent parameters. To introduce the first technique of obtaining these rules from the governing equations, let us consider the vibration of a spring mass dashpot system. There is a mass which is connected to the surroundings through a spring and a dashpot and is subjected to a periodic force F naught sine omega t. The governing equation for this system can readily be obtained as m d2x by dt square plus c dx by dt plus kx is equal to F naught sine omega t. M is the mass, m d2x by dt square is mass times acceleration, plus c is the damping constant, c times dx by dt is the damping force, k is the spring constant, so kx is the spring force, and these forces must sum out to the force which are forcing the mass to vibrate. The solution of this equation is of the form x is equal to x naught sine omega t plus phi, where x naught is the amplitude of vibrations of x and phi is the phase difference from the wave frequency of the forcing force. The independent variable is t, the only one. Independent parameters, those on which we have control and which define the problem, the uniquity parameters, are m, the mass, c, the damping coefficient, k, the spring constant, F naught, the amplitude of the force, and omega, the frequency of the oscillating forcing force. Dependent variable is only one x, and the dependent parameters are x naught and phi. X naught the amplitude of vibrations and phi the phase angle. So that the variable x, the dependent variable x, can be written as a function of t, the independent variables, semicolon, and the list of uniquity parameters m, c, k, f naught, and omega. We could also write the dependent parameters x naught as a function of the uniquity parameters and phi also as a function of uniquity parameters. Note then in both these cases, the independent variable would not be involved. The question that arises is that if we are not able to do the experiments on the prototype system, on the actual system, can we do experiments on a model system and from the results obtained thereon predict the results for the prototype system? That is the question that we need to answer. If so, how should the uniquity parameters of the model system be related to those of the prototype? And then what rules will be used for predicting the results for the prototype from the results from the model? The first technique starts with normalizing the variables. There are two variables, x and t, dependent and independent. Normalize is that we make them of the order unity, make them of order 1. How do you do that? We introduce the characteristic values of these variables, the typical values of these variables, and I define these variables with the typical values called the characteristic values, then we should get variables non-dimensional of order 1. So the normalized independent variables can be written as T star is equal to T divided by Tc, where Tc is some characteristic time. We'll talk about this a little later. And the normalized dependent variable x star is x divided by xc, the characteristic value of the dependent variable. A good choice for Tc, the characteristic value of time is 1 over omega, 1 over the frequency of the forcing function. And a choice for xc, the characteristic value of x is the amplitude. It's a good choice. With this, the equation would become this. Notice that in this equation, we have made the coefficient of this term as 1. We could make the coefficient of any term as 1. It really does not matter. And if we do this, in this equation, there are now 3 groups of parameters. These two are made up of the values of the independent parameters, and this, the last one, has x naught, the amplitude of vibrations, as the dependent parameter. And from this, it is clear that the value of this dependent parameter should be a function of only this and this parameter, which is written here like this. If in two systems the values of m omega squared by k and c omega by k are equal, that is, the value of m omega squared by k in one system is equal to the value of this in the other system, and the value of c omega by k in one system is equal to the value of this in the second system, then the value of x naught divided by f naught by k, the left hand side, should be identical. Similarly, for the phase angle phi. This equation is easy to solve analytically, and the solutions are these. You don't need to worry about how they are obtained, but we will see that x naught divided by f naught by k is a function only of m omega squared by k and cw by k occurring as they do. Note that each of these parameter is non-dimensional with no dimensions at all, no units. It is conventional to use omega n for under root k by m. Omega n is the natural frequency or the resonant frequency of a spring mass system with no damping, and that in high school was obtained as under root k by m, so that m omega squared by k can be written as omega by omega n whole square. Omega n is the resonant frequency, omega is the actual forcing frequency. And we introduce zeta for c divided by twice m omega n, so that the parameter c omega by k is equal to twice zeta omega by omega n, and we get this expression for the non-dimensional dependent parameters denoting the amplitude oscillation, and this for the phase of oscillation. Same equation. You notice that m omega square by k or omega n is non-dimensional. We give it a name pi 1, the first pi number, and zeta is equal to c divided by twice m omega n is the second pi number. These can be used as modeling rules. Two systems would have the same non-dimensional results if the values of pi 1 and pi 2 of one system is the same as the values of pi 1 and pi 2 for the second system. The dependent parameter x naught divided by f naught divided by k is a function only of pi 1 and pi 2. So, if two systems have the same values of pi 1 and pi 2, then the value of x naught divided by f naught by k should be identical in the two cases, and that can be used as the prediction rule. So, we can choose the value of m, k, c and omega of the model system in such a manner that the values of two pi's, pi 1 and pi 2 are identical, and then do the experiment on the model system. Measure the value of x naught divided by f naught by k in the model system, and this exactly would be the value of x naught divided by f naught by k on the prototype system. And since we know the value of f naught by k for the prototype system, we can predict the value of x naught and similarly of v of the prototype system. This, in essence, is the way the modeling works. We establish the modeling rules. The number of pi's would be lesser or fewer than the numbers of independent parameters, the uniquity parameters. So, it would be possible to match the pi's without matching all the values of independent parameters. The results have been plotted in this picture. This first graph on the left shows how the amplitude changes with the frequency omega by omega n, and the inset graph shows how the phase angle varies with the frequency ratio omega by omega n for different values of zeta, the damping parameter. These two graphs should be sufficient to predict the performance of any system of mass dashpot spring vibrating system, given any values of the parameters omega, k, m and c. We can calculate the frequency ratio omega by n and zeta and read from this graph what the values of the non-dimensional amplitude should be and what should be the phase angle. This is only possible through the concept of similitude. Even if we are not doing experiments and we are solving this problem numerically, we could solve it for different values of these uniquity parameters in non-dimensional forms, the two pi numbers, obtain the results, plot these graphs and use them for predicting the performance of any vibrating system. Let's do another example. And this example is from heat transfer. Let's discuss the problem of the transient conduction in an infinite slab. Let us have an infinite slab of thickness 2L and set up the coordinate system so that the left face of the slab is at x is equal to minus L and the right face is at x is equal to plus L. Let T naught be the initial temperature of the slab, and at time t is equal to 0, this is immersed in a fluid with a temperature Tf. There is a heat transfer coefficient H for the convection at the two faces of the slab. There is conductivity K of the slab material, the density rho, and the specific heat Cp of the slab material. This is an elementary problem of heat transfer, and after we submerge it, the temperature variations at any time t would look something like this. This profile will change with the time, and after a infinite time, the temperature throughout the slab would again be constant at value Tf. To predict the value of temperature at any x at any time t, we write the governing equation. The governing equation is rather simple. Del T temperature by del time is equal to alpha del square T by del x square, where alpha is the thermal diffusivity, K by rho Cp, a material property of the slab material. This equation is to be solved subject to the following initial and boundary conditions. The initial condition, T, temperature at any point x in the slab, is equal to T naught for time less than 0. For any time less than equal to 0, the temperature is T naught. Then the time T, when the heat transfer to the ambient fluid is permitted, we have the heat flux conditions at the two end. Minus k dt by dx is the heat transfer within the slab material at x is equal to minus L. And this should be equal to H times Tf minus T, the fluid temperature minus the slab temperature at the interface at x is equal to minus L for T greater than equal to 0. And similarly for the right face of the slab. One initial condition and two boundary conditions. So temperature T would be a function of x and t, the independent variables, and alpha, h, k, l, t naught, and tf, the list of independent parameters, the uniquity parameters. Let's normalize the variables, independent variables, x and t by x star is equal to x by L, where L is the characteristic length dimension of the slab, half the thickness of the slab. And T star is T by tau, where tau is some characteristic time. We don't know what it is. We'll talk about this a little later. But as of now, let's take tau as yet undetermined. We'll select a proper value towards the end. In non-dimensional time, non-dimensional temperature, when we talk of temperature, there's a simplifying feature of this problem, of any heat transfer problem, that we must exploit here. And that feature is that it is not the actual temperature that matters in a heat transfer problem, but it's only the temperature differences that matter. The heat flux depends upon the temperature differences rather than temperature. So the origin of temperature could be anything. In Fahrenheit scale, we use the ice point as minus 32, as 32 degrees Fahrenheit, and we use the same in centigrade scale as 0 degrees Celsius. The starting point, the zero of the scale does not matter. It's only the temperature difference. So let's not talk of temperature. Let's introduce theta, the temperature difference, from a reference. We could choose any reference. Tf, the temperature of the surrounding bath, surrounding fluid, is a convenient reference. So we define a temperature difference as T minus Tf. And we normalize it by dividing it by a characteristic temperature difference. Clearly in this problem, T naught by Tf does characterize the temperature difference for this problem. So we define a non-dimensional temperature difference theta star, a normalized temperature difference theta star, as T minus Tf divided by T naught minus Tf. And if we do this, then the governing equations is simplified to delta theta star by delta T star is equal to alpha tau by L square, del square theta star by del x star squared. Note that tau is as yet unspecified. The boundary conditions change to theta star is equal to 1 for all x stars and for all t stars less than 0. And the conditions at the interface, boundary conditions, delta theta star by del x star is equal to HL by K theta star at x star is equal to minus 1 for t star greater than 0. And similarly for the right boundary condition at x star is equal to plus 1. Note that this definition of the problem now has only 3 groups, or rather only 2 groups of parameters, because this HL is the same. So there are only 2 groups of parameters. If there are 2 geometrically similar situations and the values of these 2 parameters, alpha tau by L square and HL by K, match in these 2 problems, then the non-dimensional theta star as a function of x star and t star would be identical in the 2 situations. And therefore, the problem now reduces to theta star is a function of x star and t star, the normalized independent variables, and the 2 pi numbers HL by K and alpha tau by L square. From the original list of 5 parameters, now we need to match only 2 parameters to obtain similarity. HL by K has been given a name by a number after the scientist Jean Boyle, a French scientist who did work related to conduction, unsteady conduction. And this is a number that has been named after him to honor him much later. Further, let's talk about tau as yet undefined. In this problem of unsteady conduction, both sides of this equation, the governing equation in the normalized form, should be significant. Since we have normalized our variables, we expect the derivatives, delta theta star by delta t star, as well as delta square theta star by del x star squared of order 1. They're normalized. So both terms would matter only if the coefficient alpha tau by L square is of order 1. And since tau is so far arbitrary in this problem, we can set it equal to L square by alpha without any loss of generality. Tau is arbitrary. If I give it a value of L square by alpha, then alpha tau by L square becomes 1. And since it becomes 1, it drops out of the equation. And we get theta star as a function of x star t star and only one pi number HL by k. With t star is equal to t by tau now becomes alpha t by L square. This is really a variable, but is one of the few non-dimensional group that is given a name. This is named as Fourier number and abbreviated as FO, capital F and O. After the famous scientist Joseph Fourier, who derived the equation that governs conduction. And the result is so powerful that we can solve all problems of unsteady heat conduction in a slab by a set of two graphs. You see in this problem, theta star is a function of x star and t star with HL by k as a parameter. The HL by k is Bayer number with HL by k as a parameter. There are two variables. A scientist by the name of Heisler devised a scheme in which he said we will solve the first problem as x star is equal to 0. That is at the center line of the slab, and will produce the result of theta star as a function of t star, that is the Fourier number, with HL by k as a parameter. This graph, you enter at a non-dimensional time, let us say 22, and go up to the value of Bayer number, 1 over Bayer number say 5, and from this we read the normalized temperature difference here. This is for temperature at the center line of the slab. I will not explain it further, but this graph is supplemented with what is called a position correction chart. From this, we can, once we know the temperature at the center line, we can predict the temperature at any other location. You can refer to any textbook on heat transfer to understand how this graph is used. Thank you.